Hello guys, my name is Saddam and welcome to my channel. Today we are starting another topic in Kleppner series, and the topic is Approximation Method. You may wonder, what is this approximation method? In physics, and when we try to understand the real life problems, we always rely on the methods that we have. We are calling it approximation method. Because sometimes when you have the toy models, means for an example, you have the block and it is moving, if you are applying some forces and it has some acceleration. But in no time, if you are taking this block, inside the water and you are applying some kind of you want to understand what is the kind of acceleration it has because of surrounding waters, then you are entering yourself in the very much realistic situation where things are complicated, because here the viscous force is there and there are different kind of forces like tangential forces are there and forces due to water in every direction is there, and therefore it has also experienced some kind of forces. To solve or to apply Newton equation is not easy here, and to understand that how this body will behave is kind of very tricky thing to analyze. Well, what we actually does that we try to approximate this situation in more realistic, like that we want to understand this problem but not in a very realistic situation, that we want to have some kind of approximation. For an example, we can neglect the viscous force, or we may think like, okay, the viscosity force, like the resistance force from the water is low, it's not very big deal, so we can take it as little resistive force. We may analyze the situation in one dimension, otherwise it is happening in three dimensional, but we may want to understand what happens in one dimensional, and we may consider that okay, there is only one forces like force of gravity and force of water like buoyant force are there, not too much complicated forces like tangential forces and so on. We may also consider that there is a tension, surface tension is pretty kind of low and there is not too much effect on this block. So you see, we have applied so many approximations to solve this problem. Otherwise, without these approximations, this problem cannot be solved analytically. You may need some computer, then you can solve all these things. That's why to understand the real life situation in every steps or in every kind of real life, we try to use these kind of things. I hope you are understanding this thing. So let us first study that how to apply this approximation method. Occasionally in course of solving physics problem, you might suddenly realize that you have become so involved with mathematics that physics is largely obscured. Means that in physics you may understand that whatever you want to understand about the nature, you have to do mathematics, and mathematics will guide you, about the realistic situation, that how things will evolve. So that's why whenever we do try to physics, the more mathematics is involved. In such cases, it is worth stepping back for a moment to see if you can reduce the complexity, for instance, by using simple approximate expressions instead of exact formula, as I have already described the situation here, that we want to reduce the effect of some other things, and we try to understand that okay, is this working or not. You might feel that there is something essential wrong with substituting inexact results for exact ones, but this is not really the case, as the following example illustrate. You see, you may always wonder that okay, this is not the real life situation, so whatever we are applying here, maybe it will eventually be wrong. We cannot apply in real life situation. But for your simplicity or for your understanding, I can also say that the airplane is flying, the motorcycle is racing, and there are so many semiconductors like your mobile phone and all these things. In every realistic situation, people develop mathematics, and those mathematics are approximated mathematics. Okay, the real life mathematics could be very tough to understand and tough to analyze. So with the approximation, it is not just like that we are approximation 1 goes to 2, like 1 is equal to 2. It is not just like that. Okay, we cannot approximate that 1 is always be equal to 2 and 1 is always be 1 is 2. Okay, so this is not the approximation you may encounter in physics. Basically, the approximation has a different characteristic in physics, and that's why in real life situation, when we are building aeroplanes or any kind of system, maybe mobile phone or maybe any automobiles, everywhere there is a mathematics, but still the mathematics are very much approximated and it is working very fluently. So what does it mean by this approximation method? Means that you want to solve, so can you say that, okay, we want to solve some system which is very realistic, and we got very complicated structure. Maths is very complicated structure, but we approximated here, and then things get okay. And now things are like, okay, we have solved this problem. And again, this is very much realistic that, okay, it doesn't affect the system in the nature at all. We are good in this approximation. So the thing is that when we try to approximate things, we have to be very careful about this approximation. Means that how far we are taking this into our account, or do we do this kind of thing like 1 is equal to 2? So it doesn't work then. So our approximation is like 1.98, it may equal to 2.0. Okay, so this kind of approximation we are talking about, and this approximation is very much used if you are working in atomic theory and so on. So yeah, we have to understand that how do we approximate in physics, because it is the greatest tool people have ever discovered and invented in mathematics. Okay, so that is the enough motivation, and let us see what is an example. The period of simple pendulum of length L is t0, denoted by t0, and it is having time period 2 pi square root of g over L, as you know it, the time period of simple pendulum, where g is acceleration due to gravity. This result will be derived in chapter 3. In next chapter we will see how can we derive it and how can we modify for different cases, and how can we make simple pendulum for realistic situation, but not here. Okay, the accuracy of clock driven by pendulum depends on L remains constant. We are building some clocks. In our earlier period we are developing clocks based on this simple pendulum, and the simple pendulum we analyze our time system having this approximation that length is not changing. Okay, whatever the length we are using, whatever the string you are using, maybe we are using steel, maybe we are using iron thread or anything, our assumption was that this length never changes. Okay, this is fine. So but L can change due to thermal expansion and possibly aging effect. Well, if you have some kind of thread here, maybe your daytime the temperature is hotter, or maybe in Russia or in North Pole if you are living it, where your daytime temperature is, let's say, minus 70 degrees Celsius. So this will always affect your expansion, means thermal expansion of the material, thermal expansion. So either it will elongate or either it will shrink. Both things can happen. So if both things can happen, then we cannot say that whatever we are using, length is very much constant. And if length is changing, therefore t is proportional to g over L. If your length is not constant, therefore time period will also change. Maybe at 6 o'clock your time period was 0.1 second, while at 12 p.m., 6 a.m. was this one, and 12 p.m. the variation in time period was kind of 0.2 second, and which is huge. So this may lead a greatest error. And again in 6 p.m. this goes to like again 0.15 seconds. So you have a very vital error in your system, and gradually this error will increase. There is no way you can reduce this kind of error in the system, except you are taking into account that, okay, there is a thermal expansion and contraction and we have to take into account. But the problem is that how will you take into account? And this is the realistic problem. Okay, to do that, we are first writing that t is 0 when we are using the new string and we are approximating that there is no change in length. Now you put the system and you say that, okay, maybe there could be some expansion or contraction in the length. So we are writing that this L could be some changes. So like this, we have written a small l. And a small l, this change will be very much small. This is the first approximation we are using. Okay. This is the first approximation that if it was 5 centimeter, but due to thermal expansion, it could be like 5.01, 5.02. It is the first approximation and not clever one. Okay. Now but this kind of small change may lead to the error that we have already given you, that maybe it has the error of 0.1, 0.02 and so on. So yeah, but we want to analyze that how far it has changed from its true value. So how do we understand? Well, to understand this situation, what we can do here, we want to understand that how far it has changed from its real value. As you can see here, delta t, they have found that t minus t of 0, that whatever the initial time period it had. So 2 pi I am taking outside, and whatever the thing is here, like g is g over L plus L minus of the true time period. Now you will say that, okay, what should we do in order to solve this kind of problem? Well, if you're looking at it, it is like, okay, we have the kind of problem like 1 over a is minus of 1 over b. What is the solution? In your eye, you can say that there is no any solution and we don't know what to do. And then there's come the power of expansion, that okay, we may do something, because here L is less than L, because it is so far so much smaller than L. So we have to do something amazing. So what should we do? Well, we can use some technique. And what could be the technique? The technique is very interesting, that we can use the binomial expansion. And you may ask that, what is this binomial expansion? Binomial expansion, or the Taylor series expansion, you can say that binomial and Taylor series is different one, but we are now interested in binomial expansion. Say that if you have like this 1 plus x, and this x is very smaller than 1, we can do like this. We can expand it in a kind of series thing, n times x plus n into n minus 1 over 2 factorial times x square and so on. This is the approximation. So far so good when x is your smaller than 1, 1 plus 1 by x. Now you may ask that how we can apply this thing here. Now we can take it square root of g outside, and we are left with only 1 over L plus L minus square root of L. Again, what we can do here, that we have to make first quantity like this one. Then how we can do it? Well, this is very simple. Like we have L plus L, which is 1 over. So what we can do here, like if I'm taking L common outside, this one is 1 plus L over L. Now L is your smaller quantity and divided by large quantity, so this will make very smaller than 1. So what we can write here, that 2 pi square root of g, and here we can write square root of 1 over L into 1 plus L by L minus 1 over L, which is your square root. Now which is we can write 2 pi square root of g, and we can see here that this is your multiplication, so we can take outside square root of L. So we are only left with 1 by square root of 1 plus L by L minus 1. Got it? So I think so far we are doing very nice. Now how to do it? Now here L by L is your x, so it is like 1 over 1 plus x to the power half. But we have the formula of like this, everything is in numerator, so I know how to deal with the powers. So we can write here like 2 pi square root of g over square root of L. So sorry that I am using this kind of thing to express all these things, like 1 plus L over L to the power minus of half minus 1. And here we can do a very nice thing, like, now since L by L is so smaller, therefore we are not going to do in second order, because it will be again too much smaller. Convince yourself how it is smaller. So if L by L is so much smaller than 1, what we can do, we just use the linear expansion, means that we are just expressing this thing up to x, up to order of 1, which is here, like 1 plus nx, and n is my minus half, therefore it will be minus half, and x is your L by L, which is minus 1. And we have this nice result. Here it is saying 1 minus 1 is cancel, and we are left with only 2 pi square root of g by L, and there is something we have like minus half L by L. So we have this system, and we have this amazing result like this. It is saying that your time period is actually very less, which is approximated as, you can analyze here, it is your t0, because t0 is a time period, and we have this minus of 2 L by L. Now this is the error in your system, so the error will always be in plus or minus, it is always adding in your system. So there is some kind of system, there is some kind of error here. So that it has shown that this delta t is approximate is equal to minus of half t0 L over L. For instance, if L over L is 0.01, the time period is increased by 5 into 10 to the power minus 3 t0. Then you may ask that it is negative, then why we are increasing? If you are familiar with that, the total time period would be the time period t0 plus some error into it, and this error is always being adding in addition, plus minus delta t. If it is negative, negative becomes positive. So error will always add. It will not subtracted from the system. It may be low, but it cannot be subtracted. So here he has shown that, for instance, if L over the ratio of this expansion over L, the true length is 0.01, the period will increase by 5 into 10 to the power minus 3, means that this total time period would have like 0.01 second increase. Every second it will increase by this one. Now you may that after 10 to the power cube second it will increase by 1. Okay, so whatever the seconds will be, like if it is 5 seconds, then after this time period it will be 6 seconds. It will note it 6 seconds, maybe 7 seconds, 8 seconds, 9 seconds. So the error is less than the first neglected term, which is in case. So if you will consider like L by L square, then the error is again very much less. So we will have the system of the higher accuracy. If we are taking more terms, means that the more accurately we are describing our system, that how much error it has. So the more error we can analyze, then we can deal with those things like, okay, this may have some kind of vital error up to second order. But in first order, we are seeing that the error in 0.01 seconds. In second order, you will see that the error in 0.401 seconds. So in this way, the time period would be more accurate if you will track down the error. Then you can say that, okay, we can have the consistency of 0.01, maybe 0.401. Then you just fine tune your system and you say that, okay, this clock has the accuracy of 10 to the power 5 seconds. Right? In seconds, like 25 seconds, 25 into 0.001 second. This has this accuracy. So yeah, this is amazing. And this is really amazing that it can actually measure this much amount of thing. And with this approximation, it may only use like 0.01. That is the accuracy here. Now we have developed the atomic clocks, and it has the accuracy beyond 10 to the power 12 order. Sorry, beyond 10 to the power maybe 23 orders. The atomic clock we are using, cesium 133. You see, we have the experiment of gravitational waves. In 2015, it has been detected that there is a gravitational waves exist which was predicted by Einstein. You know, the sensitivity in gravitational waves detection is 10 to the power order of 1025 meters. Means that it is minus 20 or 25 meters it can analyze. Means that the inside the nucleus, if there is any kind of vibration is going on inside the nucleus, it can detect. It is the meaning of this accuracy, that how accurate our measurement is. So if we have this kind of accuracy like 0.01, it can never accurately measure what happens beyond 0.001 seconds. Now if we have this accuracy 10 to the power 5 seconds, then it can measure accurately what happens up to this one, like 0.001. So if you will talk about it, okay, maybe in a ninth of in a 0.000009 something is there, so this system can't detect. Now in gravitational waves, compared to this 10 to the power minus 25, this is very huge. It's like a monster. So it is actually inside the nucleus. If you are not getting it, you must familiar these kind of things, because I will again make the video on error analysis and things like that, that how do we analyze, how do we construct our experimental setups to reducing errors, and how do we perform our experiment, and what kind of errors are there, and how can we reduce it, because these are important things. If you are doing physics, you have to do it experimentally, because as Feynman has told it, no matter how good you are in mathematics, if your experiment is say such and such and such and so, and you have got this beautiful mathematics and it has the result of such and such different than what experiment has predicted, then you're wrong. You are simply wrong. Okay, so that is the beauty of experiment. And whenever we are interacting with nature, the experiment says that okay, this is this and this, so and so and so happening in nature, and you have to admit it. It is the fact. No one can question that fact. You may just say, okay, this is there, then why it is there? You just can understand more about it. Okay, so now we are coming to the Taylor series, and this Taylor series is very much important. Why? Because if you have some kind of function, then we can use this kind of expansion to, for an example, you have some function about some point, and you want to see what happens in neighborhood. So you can say that, okay, to neighborhood, we want to understand how this function will behave. Let's take the value nearby these points. So if this thing is converging, then the behavior will be like same, that okay, this function is behaving like this, and therefore the behavior will be same in the neighborhood. And how far this will go? So how far we are taking the neighboring point. Suppose we are taking this neighborhood points, and this function is behaving exactly, it has behaved here, then we see that this is the radius of convergence, that okay, this function has a legitimate behavior in this radius. So the Taylor series expansion is always have the circular radius of convergence. Got it? It has always the radius of convergence in a circular region. It will always, if you increase this value, it will have this much about of circular region, that if this function is behave like this in neighborhood, this will also behave like this. So if you know the function of this point, you may also know the behavior of the function at this point. And this is the idea, that how can we understand the behavior of some function. So why don't you just understand about some point, and then you can expand it, and if you will understand the behavior of here, then it is good. So this is actually using in the behavior of singularity. Sometimes our function gives us the singular behavior, but if this function is singular, what we can say that we can circle it, and we may seek that okay, how the function will behave nearby point. So we don't need to understand about what happens exactly here. We are good if this function is behaving very well in neighborhood, then we have this circle of convergence. So that is the idea simply with the Taylor series. So let us understand what does it saying us. It's saying us that if you have the function and you want to expand at x is equal to 0, evaluating the series at x is equal to 0. So if you, for an example, fx, we can always expand it like a0, a1x, this is the binomial expansion, like a2x square and so on. Now a0 is going to give you that what is happening at x is equal to 0. The function will f of 0 is only the surviving term is a0. Okay. Now what we can do is let's differentiate with respect to fx this equation, and we have the first order like a1, then 2a2x and so on. So at x is equal to 0, we will only have surviving term at x is equal to 0. We have only surviving term, it is a1. So similarly, if we do the double differentiation term, then and if 0, it will be 0, then we will have this surviving term like a2 with twice and so on. So here they say that we can analyze this a's with, if we do this differentiation like a of k is equal to 1 over k f, this is the derivative, how much you have to do derivative, and x at x is equal to 0. So that is the meaning of it. Means that we have first used the binomial expansion or power series expansion. We are calling it this power series expansion, that you are writing with some coefficient like a0, a1, a2, and they are independent of x. Now we can analyze this whatever this constant are like a0, a1. So at x is equal to 0, it means that function at 0 is a0. Now we want to have this function a1, then a1 can be realized just by differentiating one time with respect to x. We have this a1, and similarly if we do double differentiation, we have a2. a2 is nothing but 1 by 2 of f double prime evaluated at x is equal to 0. In some sense, in general, we can find that whatever the kth component we want to analyze, like maybe a3, a4, a5, like 1 by 4 factorial. For an example, it will be like a4, 1 by 4 factorial. Now you do 4 times derivative, so we will writing the 4 and do the 4 time derivative and then evaluate it at x is equal to 0, and then we will understand what is the coefficient of this. So this is the result, and this is a very interesting result. Okay. So we have this following structure like x is equal to 0. So we know this is the Taylor series expansion. So we can write here fx is equal to f of 0 plus f of 0 prime and x, and so on and so on, similar to equation 2. So there is no guarantee that the series converges, but if it does, it provides good approximations to f of x in the vicinity of x is equal to 0. Now the convergence, we have not analyzed that will it converge. Means that if we use this technique to make the series of pi, will this series work? Will this series gives the correct result of pi? We don't know, but it guarantees that if this series converges, whatever the function we are using, if this series converging, then it is a very good approximation to evaluate at x is equal to 0. Now you have if you will see this equation, it is telling you again one more thing. This tells you about a very interesting thing, that f dash x, let's say, is equal to the function you are evaluating at x, okay, minus whatever the initial thing it had, and final minus initial, and this has evaluated at x is equal to 0. So for an example, if we are taking some derivative, we have this following thing. So the derivation rule coming from this Taylor series expansion. So it is the first order expansion is actually giving you the definition of derivation. What is this again offering it? The Taylor series is easily generalized to permit expansion of fx as a power series but about some other origin. So we have specifically used here 0, but it can use for another origin, like for an example the circle has some origin here 0, 0. We may analyze this, okay, now this circle has transferred here, and origin is like for an example at b place. So 0 plus b, 0 plus b. So we can use here like for an example b plus x is equal to function we will evaluate at b plus function we will first derivative and evaluate it at b and then x plus function we will do double derivative evaluated at b and x square by 2 factorial, and so on and so forth. And this series is known as Maclaurin series. So for some function the Taylor series converges for all value of x, for other the range may be limited, so this series will converge for some value for some functions up to maybe third order it will may converge, or maybe for some series it will converge for everything. as long as it demands that, okay, this has to be smaller than 1, just like we have done something. So for an example, the sin x, if you write the Taylor series of sin x, because the range it will give you only 1 to minus 1. Therefore, this sine function will always converge. But e to the power ax, if you do the convergence test, or you will do the Taylor series expansion, it will get that x is bigger or smaller, or maybe this a has to be smaller than x. Then this series will converge. But e to the minus ax, it will always conserve if you write it like minus ax plus a square x square by 2 factorial, then again negative a cube x cube by 3 factorial, and so on. So this is very interesting result here that we are presenting. So if you do these kind of things, we will have an amazing tool in our hand, because we are carpenter in physics. So we need a different very interesting tools. Then we can slice down our problems, and to become a theoretical physicist, the playing is that are you a great mathematician or not? If you are good in mathematics, if you understand your tools, and if you understand the language of mathematics, then it is amazing. It is pretty amazing, and you will deal with no matter what it is. Okay, now series expansion of some common functions as it has been described at sin x and cos x. So sin x has some series like x minus 1 over 3 x cubed by 3 factorial plus order of something 5, and so on. And because of the nature, like in power, you can see here it is x to the power 1, 3, 5. So it is called as odd function. And another way we can say that odd function, because sine of x, and if you replace it by minus x, okay, it will always give you the minus. So this thing, if you are replacing sine x by minus x, the result will be always negative. Therefore, this function is called odd function. And also, if you do the series expansion, you can see the order, like it has the odd number of orders, x1, x cube, x5, x7. Therefore, that's why sin x is called as odd function. Similarly, we have this cos function, and it has the expansion like 1 minus half x square plus 1 over 4 factorials x to the power 4 minus 1 over 6 factorial x to the power 6. So what happens? Now you see it here, the power is x0, 2, 4, 6, 8. Therefore, it is even function. Or you would have realized now that cos of x is equal to cos of minus x, because it is an even function, and cos of minus quantity will always give you the positive result. So the approximation we can take here, like we can choose the first order approximation that sin x is x if your x is very much small. So sin x is always x, and cos x, if your x is small, we can use that. Instead of cos x, we can try like 1 minus half x square. With this help, we can easily solve complicated equations. Because for an example, if you have some kind of result like cos x times sin x, and you don't know how to do the differential, so you may get, okay fine, I am going to use some approximation like approximately 1 minus half x square, and since x is very small, that's why I am using this one, and the result will be x square by 2 and x cube, therefore it will be x4 by 4 times 2, it is 8, and with some constant, this is your answer. So this is a very interesting feature that you will understand. Okay fine, what is the result approximately if you don't know how to do anything. That's why it is very interesting to understand the physical behavior of some function if you know how to do approximate, how to play with approximation. Now one more thing is very interesting, like exponential functions. Exponential function is e to the power x, and e has the very specific value, it is called 2.718. Is the base of natural logarithm. What is log? So first of all, the log has some kind of base 2, some log have base 10, and some log have base e. And log of base e, we call it natural log or natural logarithms. Okay, the fundamental property, like for example, log e will give you always 1, just like log 10 is equal to 1, log 2 is equal to 1. So log of e into e is equal to 1. Got it? So the fundamental property of exponentials are what could be the fundamental property? So if you understand, like for an example, log of e to x. So we can always analyze that x is equal to e to the power y. So if you do what is the x, x is your e to the power y. Now you may ask that can we do differentiation with respect to y? Yeah, sure. Dx by dy is d by dy of e to the power y, and the result will be e to the power y. Now d by dy e to the power ay is, if a is independent of y, so it is e to the power ay. That is the differentiation of exponentials. Now we have the beautiful Taylor series expansion for this case. The expansion goes like this: e to the power x is 1 plus x square plus 1 by 3 factorial x cube and so on. So that's why it can be written as x to the power n over n factorial. Got it? So if n is 0 and 0 factorial is always be 1, okay, you don't have to, so it will, you will find, so x plus, hang on a second, x square by 2. So you will have x plus x square by 2 factorial plus x cube by 3 factorial. This is the series of exponential to the power x, and this is a very beautiful series. Now we have already found that, okay, how can we do this kind of approximation? Because in the previous thing we have understood the binomial series, and this is the binomial series. We have already found that you can use the binomial series to express in a power series expansion, and this result is valid for x if x is lesser than 1 or minus 1 or greater than minus 1. Got it? So this is the result. We have now differentials. Now in differentials we can use the approximation. For an example, how we have the definition of differential like f comma x, f dash of x, like f of x plus h minus the function at defined of h, means the pure function at h over h, because x plus h minus h give you h, and we have limit that this h is very near, that h goes to 0. So this is the differential formula, and we have found out from the Taylor series expansion. But in Taylor series also, suppose we have some function and we want to see how the behavior in neighboring point like delta x, and delta x, let's say very small and not too much smaller, but it is smaller. So we will have f of delta x, so it may have like f of x plus f, we are doing it x, and then we are having delta x plus f double prime x over 2 factorial and delta x squared, just like they have did here. Now delta x is very smaller, therefore we can, okay, cancel this term, like, okay, you may go out. Now we can choose here like f of x plus delta x is equal to f of x plus f x delta x. So what could be the f dash x? So we can choose here, like you can write f of comma x minus f of x is approximately equal to, like you do derivative and do this finite difference, like delta x is your finite difference, and this has to be smaller. So in approximation we can take the derivative of this thing, this guy, and we can say this is equal to f dash x times delta x. So this is a very good result. For an example, sometimes we have to use this kind of result when we don't know how to differentiate something. Like for an example, some people say that, okay, differentiate with this thing, like it is differentiated with respect to x, it is dependent on dfx. So you can write here that f x times delta x, that okay, this approximately will be equal to delta x, and you don't know what is delta x, so delta x is nothing but x at some point I plus 1 minus the initial point, that is this one. So this will help a lot in the numerical analysis, or it will if you want to analyze the system. Like otherwise, for this guy we will learn here, like df, if you are actually using the differentiation function like df, and f is dependent on function x, so it will be like f comma x, f is differentiating with respect to x and dx. This is the true formula of differentiation. Okay, now we can analyze. You may ask that what happens if f x and y is dependent. So you have to write here like f df by dx times dx plus df by, so it will be partial, it is not completely derivative, it will be, you have to write here dy, and so first this will have the derivative with respect to x, and secondly it will be a derivative with respect to y, and these derivatives are partial. not complete derivative. So this will be equal to this one. But again, we have this beautiful approximation that we can write, okay, fine, no problem. We can write here that, okay, this is derivative with respect to x, and we are using delta x, plus this is derivative with respect to y, and we can write here delta y. And you may now have delta x and delta y, but you could not have dx and dy. You may think, okay, fine, kya main loon? What should we take delta x and delta y? So here they have shown that we can always approximate as df over dx, and if x is very small, like d delta f over delta x. Got it? And this delta f is the change in function. It is not derivative. It is a change in function, delta and this one. So if you are taking the limit, like limit this change is very smaller, then this will have the same result, like delta f by delta x. It will be equivalent to df by dx. But if we are writing here df by dx, and we are just using approximation, writing delta f by delta x, they are never be equal, but they are approximately equal. So this is the very interesting feature of calculus that we have to understand. And now another thing is the significant figures and uncertainty and experimental uncertainty that we have already described. That we have to, whenever we are designing our softwares or designing our experiments in physics or in chemistry or in biology, we have to have error in our function, in our experiments, in our softwares. If the error is large, then the code will completely abrupt. There is no viability of this software. The result will corrupt. So whenever you do calculation, you have to have that whatever you have given the result, this has to be the less error. The error must be less. So there is some percentage of error which is valid in physics, because that error people cannot ignore, and we are calling it that 5% sigma error. If your result is accurate, if your result is this one and your error is 5% of sigma, then it is completely amazing, because the result is, whenever you do if you are doing the 99% time experiments, you will get this result. That is the surety. So 99.95 times you will do this experiment and you will get this value. And if your result is more than 5% sigma, then it is like that, okay, there is no chance that if you perform repeated this experiment, then this result will not meet. So whenever we do experiments in physics, like do the time period, find out the time period of simple pendulum, or using the simple pendulum, find out the value of g, and already Newton and other persons in laboratory, they have already given that, okay, g is 9.8 and so on, 9.86 and so on. Then why people have sure that this is the good value? Because whenever they have performed the experiment and when they shown the result to the people, they have, their experiment has this 5% sigma level of confidence that their result is 99.95% accurate. If you do many time experiment, you will get this result. Now the students is asked in college that, okay, perform this experiment and you see that how close you are. And if you will say that, okay, sir, I have got 9.4. Okay, and you may think that, okay, I have got a very beautiful result at 9.4. I have done this experiment very accurately. So this 9.86 is wrong, and you want to that, okay, I want to then I have revolutionized. Somehow in our geographical condition we got 9.4. Now they will say that, okay, you are living in the surface of, so you will not get a good marks. Out of 10 you will get 8, because you have not performed an experiment very well. Your performance of experiment is poor, because this is the confidence of 99.95. This says that no matter how much you will do experiment, your solution will be always like, it will have 81291. You will never get 9.4 unless and until something has abruptly gone wild, that maybe some outer thing influences, and you got this kind of gravity, and so there is kind of a very catastrophic situation going on there. Unless that thing happens, you will never find that 9.4 is your very good result. Therefore, based on these things, professors and all these things, they used to give you the marks that okay, you have done a great experiment or you have performed very poor experiment. Okay, that is the motto of repeating what is already happened several years ago, and you are performing this experiment so that you will understand all these errors and so on. Okay, so let us read it out. When performing a numerical calculation, it is helpful to have a clear guideline as to the accuracy with which the calculation should be carried out. In other words, we should retain only number of non-trivial digits, significant figures. Example of significant figures, like here the significant figures are 3.1415. So we have the significant figures like 1, 2, 3, 4, 5. So here we have 5 significant figures. In gravity, the significant figures are 3, 9, 1, 2 and 3. In 9, if we are written 9, so the significant figure is just one significant figure. If we have written here like, this is amazing thing, like 0.00, 1, 2, 3, 3 times 0 and 2, 1, the significant is 2. So we don't consider here these zeros. We consider the value more than zeros. So whenever we write like 0.009, the significant digit is 1. Got it? So we don't count these numbers. But if we write here like 0.90, then significant number is 2, because these values will count. That it is, if you are writing 0.90 means that there is something again there. Maybe in some experiment it will be 9.1, maybe it will be 9.3. That's why it has been written. It is that significant figure is 2. So whenever you report your result, you have to mind it how to report your result. This is very beautiful thing. You may realize that okay, this is nothing, but yeah, this is a very beautiful result. So leading zeros don't count, but trailing zeros too. Like here 0.000, 210. Now here three significant figures. So 210 is a significant figures. Maybe in some, maybe if we were to repeat this experiment, we will get 0.000212. So whenever we do maths, we ignore that okay, this zero has no value. But whenever you do physics, you mind it. This has amazingly, created implication. Now you don't realize. Mathematicians don't realize it, but physicists, we do realize. A useful rule of thumb that the number of significant figures retained in result of calculation should equal to smallest number of significant figures of any number of calculations. For instance, if the acceleration of gravity is calculated taken to be 9.8 meter per second square, the result of calculation should be quoted no more than 2 significant figures. Now what is the meaning of it? Suppose you have a meter scale and you can just measure like 0.1, 0.2, 0.3, like here 1, here 1.1. So now people have given you this scale and you found this data 1.1 plus 1.21 plus 1.333. Now you have this meter scale and you found this result, and they will ask it okay, add it. So what you're gonna do here, you simply add these things like adding like 3, 2, 5 and 1, 6. So first of all you have to write here let us say 0 and again 0, again 0. So here is 3, 3, 1, 4, okay, 3 to 5 and 1, 6. It is 1.643. But we know what is the least thing, right? The least one is 1.1, because this meter scale can measure 1.1 only. And these values they have given, they are making us fool. Maybe they have taken some other data. Maybe there's some line fallen between this and this, and you may say that okay, this may be like close, like this is 1.2. So we are saying that okay, this is 1.21 maybe. So we do this kind of thing, but we never realize what is the harm. Because this result, this meter scale can only measure up to 2 significant digits. It can measure 3 significant digits. So we have to make it 2 significant digits. So we will drop these guys and we will write that this is 1.6. So it has the confidence of only 2 digit significance. It doesn't have confidence of like 4 digit significance. So that's why we have to rely which one is shorter, which one is very less. So this is the implication. So therefore here they have said that experimental uncertainty can be expressed in several ways. For example, this guy that I have already told you that, for example, you are measuring A, so A plus delta A, plus minus of something. or concisely as 72.53, and there is a error of 20, that whatever you have measured in this last significant digit, you have this error of 0.20, means that the result can vary like 72.73 or 72.33, means that if you do billion time experiment, your result will fall inside this result will fall inside, that is the accurate people have measured, or you have done this experiment, that this will have to fall under this thing. Okay. Now another way is the parts per notation based on fractional error. The fractional error in our example is 0.20 by, so this one is fractional error. What is the fraction of error? Like whatever the error you got, and we simply divide by it, and you will get whatever the value it we call is fractional error. An error can be stated as 2.8 parts per thousand, because 2.8 parts per thousand. So in thousands we have 2.8 per thousand, alternatively 2.8 part in, because we are always writing this fashion, so it is just way of saying. So this is the way we can use, you can find out fractional error, and this is the meaning of significant figures. I hope you understood the underlying meaning of these things, approximations, how to do it using binomial, using Maclaurin series, Taylor series, why do we do it, how to approximate different derivatives also, and how to do integration from using these kind of very approximate things. And based on this approximation, we understood that there is a greater implication in whenever we perform experiments, and we have to track our errors. Therefore, to find out the errors in our system, we have to understand the significant figures. So if you like it, please give it a thumbs up and share to your friends. Thank you very much. This is Saddam signing out.